first thing is the homework problem. Number 3, we have performance index. Then and I'll replace u again by minus k and x. So this j will equal to 1/2 e. I'm going to make this alpha t like this and then put alpha t here. And then now the this part will be like this, x transpose u and x. This part is kx, this part will be x transpose and k. And accordingly I can factor out the x transpose this side and the x to this side. Then I'm going to come here and x is time function. X is time function. So is this multiplier. This multiplier is time function. So I'm going to call this one name. And this will be its transpose. Because e to the exponential alpha t is a scalar value. So this will be the transpose. So I'm going to call this y transpose dt. And then now I'll say for the closed loop system to be stable, then we'll have minus q k transpose rk is equal to d by dt, the t, and then exactly like what we've done in the LQR. Now I have here y and y transpose, so I'm going to make them, instead of the x and x transpose, I'm going to make this y transpose and y. Then the rest straightforward. So now I come here and I look at first the d by dt, y tp, y. So this will be y dot p y plus y p y dot. Now the y is not simple function anymore. It is two time domain functions. So the derivative will be the derivative of the first times the second, plus the second times the first, and so on. So I'll make this will be easier. This will be x dot e to the alpha t plus alpha x e to the alpha t. And then I have t. And then this y transpose is x transpose e to the alpha t. And then the same story here. This is x e to the alpha t times p. And then the first part is two parts. X dot e to the alpha t plus alpha e to the alpha t and x. Now I'll replace x dot from the equation of motion. And then now you'll see here I can factor out e to the alpha t. e to the alpha t. So I have e twice alpha t. So now this will d by dt, y transpose p and y will equal to x transpose a to the minus b k transpose plus, I'm sorry, yes, this is correct. First term is correct, and then times this. So this times p and x, and then e to the 2 alpha t. The second term will be x transpose this whole thing should be transpose here. So this will be x transpose, and then times alpha p, and then times x times e to the 2 alpha t. So the first part is done completely. And then the second part of the same story will have two terms. The first term will be here x transpose p, and then the x dot are replaced by a minus bk and x, and then I have two exponentials, e to the 2 alpha t, and then the last term is here. We have x transpose p, then alpha times x e to the 2 alpha t. And now this whole thing should equal to minus, we made a mistake here also again, y transpose and y. So the y transpose will be x transpose e to the alpha t, and the y will be x e to the alpha t, and then the in between and then now we have this term will drop from the two sides, and then we have x transpose in each one of these terms. So the result will be x transpose. Well, we don't have to write the x transpose, so now we'll write the a minus bk transpose on p plus p a minus bk, and we have one of these and one of these. So I'll break them down here, put one here and one here. So here plus alpha p, then this whole thing will equal to equal to 0. Then you group them. So we'll have a plus the alpha I minus bk transpose on p, and then p a and alpha. So this would be a plus alpha I minus bk equal to 0. Now, if we have this condition, then I can take this and plug it in J. When I plug this in J, then now J will be equal to 1/2 integral minus d by dt y dt. And if the system is stable, then y will go to 0 at infinity, and this will just reduce to 1/2 y transpose at 0, p y at 0. And optimum, del j is equal to 0. This will imply that del p is equal to 0. And from this equation, we do as we done in the LQR. Now differentiate. This depends on k, so this will be del k times p. Then differentiate with respect to p, so this will be k del p. Same. Everything will be exactly the same, so this will yield, after the variation, will give us the same k as we had before. R inverse B transpose and P. So the only difference is we replace our A by A plus alpha I. The whole thing is this term if we have delay in the system. So if you try to implement a controller that has time delay, then you put penalty on the delay here. And from this, you can extract the equivalent controller forming the Riccati equation. And the only thing will be different is that we change the A to A plus alpha A, which is the amount of delay that we have in the system. Okay? The first problem and the second problem are straightforward and they look the same. Here we have a system that looks like this. In the homework, we said the A looks like this.
Minus 1 by...
The reverse, 1 over m here. Okay. And the B is like this. In the example that I gave you last time, A looks like this. And the B looks like this. 0 and m. So these look very similar problems, but here I have the spring and the damper are uncertain to me. I have uncertainty in both these physical parameters of the system. Here I have uncertainty where I locate the actuator. So this is very common in many problems. You know, like I know the system approximately. The stiffness can change, the damping can change. Here In large system, you say I'm putting the actuator at 1 meter from this end. That's what you think, okay? But actually, maybe you put it at 1.05 meter. So you have deviation from where the physical modeling location was, and you have some error or uncertainty of where you locate the actuator. So these two can create all these loss of robustness of the controller. So the two look very similar, Now, how to design this? You know, like we look at the nominal system. That's what you think you have on your hand. So the A is an A. And the B is this B. And then you design the system. Everything is designed for this case. So for the LQR, you put the A that you have, the B that you have, the Q, and the R. And you determine the gain. And the same for the LQG. I'll use this, and then I get the L, A transpose, C transpose, U0, and R0. Now I'll use these with the actual system. Okay? But one very important thing is if we have x dot is equal to ax plus b u, and or I'll just take these and replace it by minus x hat. Okay, so now we have x dot will equal to ax, and x hat dot is equal to a minus LC x hat plus LC and x. Now if I want to plot Nyquist plot, we said this will be, I have to determine the numerator and the denominator of the open loop. So we'll use here the open, and this means u is equal to 0. U is equal to 0, so I don't have this term, oops, and this term. Well, let's take it from here also. Okay, for the open loop, u is equal to 0. Now my system will reduce to this case. Of course, I have here another terms because of the noise and disturbance, but I'm not going to put them in. Okay, so now I have the system, looks like this. And then I have here A, I have LC, A minus LC. Now, if I don't have the observer or the kernel filter, L is equal to 0. This will be 0. And the matrix will be the A and the A, which is the original system. So now I have my system like this. When I put the observer, the system matrix change. And the description of the entire system is in this form. Okay? Now, after I come and take this from state space and put it in the numerator and the denominator, I'm getting the numerator and the denominator of this assembled system in the open loop. If I'm using the LQR, I don't have this equation with me. Only thing I have is this A. So for this A, I'll get the numerator and the denominator. And then now I can look at Nyquist plot. After I get this and use the state space to transfer function command, I'll get the numerator and the denominator. Now I want to plot the Nyquist. Then I come and say the gain times the numerator and the denominator. Okay, one important thing again here. Let me put the B again here. This is my physical system. This is the filter equation. The physical system has A like this, but has B like this. This B is 0 and M, because the physical system might have uncertainty where I place the actuator. The filter is equation. I run it inside the computer. So this equation, I know exactly where I want to put the actuator. So this B is not this B. This B is 0 and 1, exactly. But this B has uncertainty, because the physical location is unknown. Okay? So if I want to look at the A and B for this system, this B has exactly the same number, 0 and 1. This B has the uncertainty of M. Now let's look at the handout that I gave you last time. Okay, so this is the nominal system. I'm going to calculate the gains again. For the nominal system. The gain for all the cases for the nominal system. So now I'm going to calculate the gain for the LQR. That's the gain that I'm going to use for the LQG. Exactly the same. The filter, here is the gain for the nominal system. For the nominal system. Everything is exactly the same. Now I'm going to go and calculate now the transfer function of the LQG. It's right here. A 0 LC A minus LC. So that's A 0 LC A minus LC. Now the B total, this I don't need it, but the B total, this B has error, but this B does not have error. So the first B has error, the second does not have error. The observer, I know exactly where it is. Okay. Now I go and get the transfer function of the system for the A and the B, the C and the D. I have this. Okay. Forget about this line. Now we will do it after we do the LTR. Forget about this line. And then now I go for the LQR, get the transfer function of the LQR. The A is known completely. The B has error, which is the how many percentage error. Then now I do this, get the state transfer, state space to transfer function, get the numerator and the denominator. Now I go to this stage where I want to plot now the Nyquist plot. So I take the numerator and the denominator, multiply times the control gain matrix. And then now we have everything that we've seen before. So again, in this example, because we have single spring mass system, you need to do a lot of damage to it to make it unstable, okay? Because it has good damping. This system has damping of 0.5, so it's very high damping, and it's a single degree of freedom. So I had to change 50% to start seeing loss of an instability problem or loss of the phase margin. But if you have very large number of degrees of freedom, very small disturbance in any of the parameters will make the system go unstable very fast. And we'll do this after the exam. Okay, so you can have more degrees of freedom, and you will see any disturbance in some of the parameters can make the system go unstable very fast. So now the LQR is touching the forbidden zone for stability. We satisfy the Lyapunov equation. Now the LQG, once you put the observer and you start predicting what you don't measure, then you start losing robustness. You start losing gain margin and phase margin. And
Can I ask you a question?
yes, ma'am.
I'm not very good with Nyquist plots. I've been using them. So
Okay.
what about that would make it unstable? Is it the amount of times it crosses the circle, or the fact that it crosses the circle, period?
We're saying now, like if I am in this case,
Yeah.
the LQR, then I am 90, it takes me 90 degree to delay the system 90 degree to bring it to the unstable zone, which is the 180 degree, minus 180. Here, it will take much less. And when you have more uncertainty, then you cross at this point. So the amount of phase margin is no longer 90 or 80, now it's maybe 60. And then more uncertainty, then bring us more inside. More inside. Now how this will be translated, if you have a system that you run analog, that's what you will see. But when you start running the system digital, you are making delays, because you have to sample and wait, sample and hold. It's called, you sample and wait, and then you sample again. You sample and wait, and so on. So if the amount of wait that you wait is very big, you can create very large delay in the system, and you can eventually come and hit the 180 degree. The delay will make the system go unstable very fast. Okay. So now, the same applies now for the homework problem. All what you have to change is the A matrix. you do the gains of the filter and the controller for the nominal system. When you do the state space to transfer function, you have to look at the system that has the uncertainty. Okay? We don't have to plot Nyquist plot. You can also look at body plot. And you have the criteria for the stability limits for the body plot. Yes, ma'am.
In the Nyquist, I thought you said you use the open loop,
Yes, ma'am. This is the open loop.
but why is being in there then?
Why is what?
In the Nyquist.
You multiply times the gain, and then you multiply times the gain.
Okay, in the Nyquist command, I'm confused. In this, we've taken the B out in the MATLAB Nyquist command, we put the B back in again?
No, because you have to write down the system description. The system, where is the actuator located? Okay, so you have to write the description. But we will not use any controller. We will not use any controller. Okay, yeah, what I'm saying is that we don't have to use this. We can also use the body plot and look at the gain margin and the phase margins. Okay.
So Dr. Foss, you said M equals 1.5 is 50% uncertainty?
50%.
Well, what's M equals 0.3?
0.3?
Yeah.
No, 0.3 is in here. Instead of 1, so the damping will be 0.3. So the damping is less, but here the mass will be, the stiffness will be much higher. Now again, for your question on the open loop and the closed loop, the state space equation again is x dot is equal to ax plus bu. And then the u is equal to minus k and x. And this is my x, and this is r. And this is negative feedback. If r is equal to 0, this term will disappear. And I'll take x multiplied times h, which is my k here. And the result will be at this point. Whatever comes here at this point is u. Now this will be the transfer function between x and u. Okay. Now how would I get this? I go here. I take the Laplace, so I have Si times x is equal to ax plus b cap u. And then now I transfer the x's in one side, and then equal to bu. And from here I can get x over u. or the transfer function will be SI minus A inverse times B. Or because of the matrices, there is no division like this. So this would be my X, and then this is U, and the yellow term is nothing but my G. When we plot Nyquist, I plot, so I don't need this anymore. To plot Nyquist plot GH let's say here vary the frequency omega and plot the real versus the imaginary parts of G and H. Okay. Now, in our problem, we said now just get the G, because the H is a constant that we multiply by it. The H is a constant. So get this G. So now to get this G, this is my numerator and denominator. And then after you finish this, which is the forward loop, you multiply the result times K. Because this is my H. I'm not plotting 1 plus GH. Body diagram plots 1 plus GH. The closed loop takes the closed loop system. So this gives us this plot. If we said, for example, like this. Now this with whatever gain that we have. And then this is the point minus 1. How much would I increase this gain until it hits minus 1? This would be my gain margin. So now I'm plotting this plot for the G and H. This is the numerator. Denominator multiplied times the gain of the system. And then this gain, how much can I increase it until this crossing point comes and hit the minus 1. So this will give me the gain margin. So this is a gain A, and the gain margin Okay, I think we've done enough on this. And then we'll do more of these now. More of these block diagrams now. One more thing about the, I think the first and the second problem. We had just a little note here. J looks like this. That's what we used to. And then we added this term, and the term in between, which is nu. This is the absolute vibration of the structure. This is the absolute control action. How much voltage I put in the system. This is how much the U is how much, for example, voltage or power we put in the actuator. Here is how much is the vibration energy. This is a cross product term between them. U is the force. X is the displacement. So the product of these two is the work done by the actuator on the structure. The more flexible the structure is, X will be very large. And the U corresponding to it will be also very large. So now if I want to do the control, I can bring the voltage down, and I can also minimize how much work I put on the system. Because the total energy is vibration energy. And how much voltage you can afford to put on your actuator, and also how much work you can do on the system. This is redundant in most cases, because the U is implied here. U is equal to minus kx, which is function of the x. But in many cases, if you have very flexible system, you might need to put something like this. You might need to put something like this.
It's
And
actually twice of x percent U.
exactly, exactly. You can move this to this form.
No, I'm saying there's 2 over there.
Oh, you mean 2 here? Yeah, it's fine, no problem. Yeah. Okay. And in MATLAB, if you look at MATLAB, then you will see that this is one of the general forms that they have. So when you say help LQR, that's what you will see. Okay. Now we'll do the LQG. And this is loop. Again, the main objective to make the LQG behaves like LQR in spite of the fact that we have only small number of sensors to measure the system response. And this is equivalent to the use of a Kalman filter. And by this, we mean as infinite gain margin and phase margin at least greater than 60 degrees. So now what we've seen is when I have an LQG and I have some uncertainty in the system parameters, I start losing these parameters, these stability margins. We will show which very simple transformation. I can make this LQG recover the properties of LQR. And we'll do it by just adding this loop transfer recovery, very simple routine. But the math is horrible, but the final result is very nice. Okay? So, until we get to where we want, we'll be a little bit tired. Okay. So now we'll begin by looking at this LQG. Again, we have x hat dot is equal to ax hat bu plus L, and I'm going to make this c x minus x hat. And of course u is equal to minus k x hat plus r. Now I'll put everything in the S domain, Laplace domain. So we have x hat here and x hat here, I'll combine them. And I have x hat here, I'll combine all of this. So I have Si x hat is equal to A minus LC x hat plus BU plus, and I'll just make this L and Y. Combine these two to Y. Now from here and here I combine these and I have x hat will equal to Si minus A minus LC inverse times x hat, oops, plus Si A minus LC inverse L and Y. I'm going to multiply this times minus k and add to the result r. So now this becomes here u, and let me make also this u here capital U, and this y here capital Y. Because these are in the Laplace domain now. These are, well, we might as well make this and this. This is the time domain, and then now I'm going in the Laplace domain. So all these are u of s, y of s, and these are u of t, and then this is all of t. Okay, so we have, I multiply by minus k and add r. So I have here plus r, and then I have minus k Si minus A minus LC inverse B and U minus K Si minus A minus LC inverse and L and Y. And I'm going to say that U now is equal to minus H U times cap U plus or minus HY cap Y plus R. And now we see here where the HU and the HY, these are equal to K Si minus A minus LC inverse and B K inverse and L. And I'm going to simplify this like this. gonna call this whole thing V 0 and B, and then this would be K V0 in L. My system is x dot is equal to ax plus bu. So from here we can say that the same story will apply Laplace and then get the relationship between x and u. So this will be here x will equal to si minus a inverse times v is equal to u. And then I can if y is equal to c and x, then we have y in the Laplace domain will equal to c si minus a inverse and v, and then this would be my u. This is my system, and this is the y that I will get. This is the u that I'll put in the system. From the bottom equation, we have c, and then b, and then I have si minus a inverse, and I'm going to call this phi. Now I take the y, multiplied times hu, I'm sorry, hy, take the u, multiplied times hu, sum both of these up. This is what we have. Subtract them from the reference command R. And the result is the u. Result is the u. I'm going to, like this is my, again, the G, the system. I'm going to combine these two in one transfer function. Okay, so I want to relate the y and the u. I'll put these together. Again, from here, I can say that 1 for I plus hu times u is equal to minus h y plus r. And for vibration purposes, R is equal to 0. And now I have relationship between these two parameters. And I can extract the U by inverting this matrix. Again, U, keep in mind that this is equal to minus I HU. We put it like this. And the whole thing is inverse. HY is K. Is 0 and nothing. And then the result. Multiplied times y. And I'm going to call this minus K, L, and y. I'm going to repeat the same diagram again, but now here I don't need all this. And we took this out. R is equal to 0. The minus still here. So now here, I put inside this box the scale. Now for the LQG, this is my system. I am measuring only small subset. And then I'm using this with the filter to get the y, generate from it this control action, and feed it back to the system. Okay. Now this system looks to me like, I need all these. Loop. This will equal to KL, CB, and B. This is for the LQG. The LQR. My system look exactly like this, except the C is identity matrix. And I'm measuring the X. I'm feeding back here the K, and negatively my R is equal to 0. Now for this case, my LQR loop we call it loop S. So I have it in the notes, so it's a pretty stupid name, but okay, K, and then phi and B. And our job is to look at this KL and C and try to make them like this K. if we do this, we can recover completely the k. Because the last two terms are exactly the same. Okay, and again the KL was I plus k phi 0 and b inverse k phi 0 and L. So now what we want to do is make this looks like this k. And we will select the L such that this whole thing reduces to this k. Once you look at what we have here, then this L, which is also inside this phi 0, which is here. Phi 0 is this. So this depends on where we put the sensors and the gain of the Kalman filter. So now from here, we'll try to make this whole thing where we put the sensor, how much is the L is, and then how to relate it to the K of this system. And I'll do this after, I'll do it next week. Let me just do one thing here. We've done poles and zeros for collocated and non-collocated. Sensors and actuators. We've done velocity feedback. For both these two cases. Then finite element. Model reduction. And then we've done LQR, full state, feedback, and output feedback. Then we've done the LQG. So the exam will have one problem of each. Is that fair? Too much. Too much, huh? Okay. So we'll have one problem from here, and then one problem from here. Okay? That's fair. So we'll have one problem finite element, one problem LQR. Okay, we have 4 homework that covered all these in great detail. The LQG, your hands are not yet 100% because you have to make Simulink of LQG, then you know it by heart. So we'll do one homework on LQG by Simulink, and we'll couple it with the LTR. This will be on Monday here from 5 to 6:15. Bye, have a good evening. We'll see you. So this will be very good for you, Mario. Huh? So you, okay. Again, here the main purpose of this is to modify the LQG controller. In order to recover the robustness of the LQR. Okay, and what we done last lecture, we said the Kalman filter look like this. Or in the Laplace domain. We'll have Si minus A minus LC, all operating on X hat is equal to B, and then cap U, L, and cap Y. And this is the Laplace of the time domain signal. And from here, then X hat will equal to Si minus A minus LC inverse B and U and inverse L and Y. And we have the control law is equal to minus K and X hat plus some reference. We call it small r. So now to calculate U from here, then I'll multiply this equation by minus K and add to it the R. Then we have U will equal to minus K Si minus A minus LC inverse and B have U then minus K Si minus A minus LC inverse L and Y. And I combined all these in one term, all these in one term. And we have here plus R, which is the Laplace transform of the small r. Then we call this HU minus HY plus R. And in case of vibration control, or let's make it first the block diagram for this case. This is the Y. And then this is the U. And then we have here H U, and hy. I combine these two. And, feed them negatively. And subtract from the r. And this equation will give us this block. And for LQR, we have the system equation. X dot is equal to AX plus BU. Then in the Laplace, I can write again X is equal to SI minus A inverse times B times U. This equation transforms to this equation. And this looks like this now. I have SI minus A inverse, and B will give us the X. This is the U. Then I'll take the X and feed it negatively through the control gain. And the same story if we have reference or zero reference in case of the LQR. Then this equation give the transfer function of the system, this equation of the controller. I'll just make here a couple things. Let phi is equal to SI minus A inverse, and phi 0 is equal to, this is small s Laplace. Inverse. And now this block, the LQR, and B, and this is X, and this is negative. And the GH of the system is equal to K phi and B. Now this is the phi and the B.
Minus K
Okay, I'm sorry. The phi and the B. And the result is X. If I want Y, then I multiply this times C. So here I can put here, if I want from U, get the Y, and this is my structure. Then I have the phi and the B will give me X. I want Y, then I multiply times C. Now I'm going to do the same as the LQR. I'm going to make this R equal to 0. When R is equal to 0, this term will drop out. And then I'll group the U's and the Y's in one side and the other side. And we'll say here, when R is equal to 0, then I have U will equal to minus HY cap Y. Then I have I plus HU inverse. And this, I'm going to write it like this. U is equal to minus KL and Y. So now I can take this and draw it here. And the GH for this case, oops, will equal to minus KL CPMB. Now these two are the same. So I want to make this look like this. So the once you set any sensor location, I want to make the KL, which is all this combination, look like a K. So we can recover the system. So if these two are the same, then we have recovery of the robustness. Again, KL was equal to I plus HU times HY sorry, then HU now is this entire term, and we put this as phi0. So we have K SI minus A minus LC, the inverse, and then B, and then the whole thing is inverse, and then HY is what we have here. Is again K and phi 0. And L. I'm going to look at this term now. And before we look at this term, put here a side note. And this note is called the famous inversion lemma. And you can see this in any matrix or linear algebra book. And it says if we have A plus B plus D inverse C, and the whole thing is inverse, so then this would equal to A inverse minus A inverse B inverse B inverse C A inverse. And the proof of this is very simple. Multiply, and you can multiply either before or after, post or pre. By A plus B, D inverse C. So of course the left hand side will equal identity matrix, the right hand side after little manipulation will equal to identity matrix. Then this will yield identity matrix is equal to identity matrix. This is very important in control, and it's used almost everywhere. So we're gonna use this here. We're gonna make the A is my I, and the K is my B, and the B is my C, and then D inverse is this D inverse. And then I just write down this expression now. Okay. I'll add these in case I this is my HY and HU. Then now KL becomes equal to, I'll replace all these, so it ends up like this. The A is identity, so the A inverse is identity also. So this will be identity minus, and then identity and the B I replace it by the K. So this becomes K, and then I have SI minus A minus LC okay, and then the last term okay, and then here we have minus okay, the C is the B, along here, C, right here at the end, we have B, and then we have the K, then the V0, there, and we want to fill the in-between, so this is the D is SI minus A minus LC. And then I have to add here the C is B and the P is K. So this is B and K. And we have minus here and minus, so it becomes a plus. So I'm going to make this minus times minus. So this will reduce to SI minus BK. And then the whole thing will be inverse. Oops. Okay, now I'm going to clean this equation and write it like this. I'm going to write it like K here, and then SI minus A minus BK minus LC inverse times SI minus LC minus BK B0 at that. Okay, now if you look at the first term times K times phi0 and L. So now if I take this orange parenthesis and multiply it times this would be identity times K times phi0 and L. So this is this first term. Now the second term is now K times this parenthesis or this bracket, which is this, times the B times the K, which is the B and the K, and then phi0 and L. Okay, so this is just a little trick. Why? So we can cancel this with this. And then now if we look at SI minus LC, so it is this matrix, but without the inverse. Okay, so now I can rewrite this as K SI minus A minus BK inverse, and this term is this without the inverse, so this becomes phi0 inverse, because we defined phi0 with the inverse. So without the inverse will be this, and then we have phi0, and then we have L. Okay, so these two will drop out, and this will equal to K SI inverse and L. Okay. You still need the inversion lemma again. This anymore, and KL equal to K SI minus A minus LC minus BK inverse and L. Okay, we'll make a little here again. Let P C is equal to SI minus A minus BK, and the whole thing is inverse. Then phi C inverse will equal to SI minus BK. Then KL will equal to K, and the inside will be made of this term and this term plus LC. So we have here plus LC and then SI minus A minus BK, and the whole thing is inverse, and here times L. So this will equal to K, and the term between the green brackets is the phi C inverse and L. Now I'm going to write this as phi C inverse plus A LC like this, and this whole thing is, I want to get its inverse. So I'm going to write here identity matrix I, and then use the inversion lemma again. This A is this is the B, this is the C, and this is the D. And then use it to expand this. So when we expand this, it becomes equal to K and then phi C minus phi C and L I plus C phi C L inverse, and then C and phi C times L. So this is just translating the matrices to here. And now we can clean this. And then KL will equal to, again, K. And then I'll factor phi C here. I'll put phi C here. So this becomes, sorry. And then also I have the L here. I'm going to factor this out also there. And then this would be identity minus identity plus C, phi C and L inverse. And C, phi C and L. So we have K, phi C and L, and then we have C, phi C and L. Now from here, I'll get this out. And this will equal to K phi C and L, I plus C phi C L inverse. So the inside now will be I plus phi L minus C and L. And this will drop with this. So this now reduces to K phi C and L, I plus C phi C and L inverse. Now we want to get to this point. We have KL completely defined. Now to get the entire thing, I have to multiply by C phi and B. Then the GH will equal to K C phi and B. Now this depends on how we calculate the L. We calculate the L now with very little trick. Now we'll say here alternate way. The gain L. We are using L from the solution of the Kalman filter equation, which we found it to be P C transpose R 0 inverse, where the P0 solves the following Riccati. A plus P0A transpose minus Q0 minus P C transpose R 0 inverse C P0 is equal to 0. Now I'm going to make this a little trick now. So we solve this. If we have the A of the system and the Q and the R and the C, then we can solve this for P0, put it here, and calculate the L. Okay. Now we'll say here let Q0 is equal to sum Q bar plus Q squared. This is a scalar positive number, B and B transpose. Or we can put any scaling matrix in between these two. Okay, the scaling matrix between these two will be a scalar, because the B is, no, it doesn't have to be scalar, I'm sorry, because it depends on the number of actuators. But if we have single actuator, then this would be a scalar. So I can put it like this, or I can put any scaling matrix. Okay, now I'm going to plug this here, and then vary the Q, vary the value of Q. So now then we have A P0 minus Q bar minus this should be plus Q. And then this is the minus P0 C transpose R0 C And then I'm going to divide the equation by q squared. So this becomes a p0 over q squared. Okay, now I'm going to increase q until it goes to infinity, or a very large number. If q is large, then q squared is very, very large. Then I can drop this term. I can drop p over q squared, because the p0 over q squared will be a very small number. And I can drop this, and I can drop this. But p over q is not as small as this. So the result will be what we have here. So this now says okay, we need all this. So now this says that B transpose will equal to P0 over Q C transpose, and then I left here R inverse and inverse, inverse and inverse. And this R inverse, I'm going to write it like this: R0 minus 1/2 minus 1/2 C over Q. Because from this you can see that this is one term, and this term is its transpose. Okay, then now we can say that B will equal to P0 over, or P0 will equal to Q B to the minus 1/2. And L, I can now calculate it. Did I make a mistake? Okay. Zero. Okay, this is here is correct. Okay, let me go back a little here. Until here we're okay. And then we'll just make this here P0 over Q C transpose, and then R 0 minus 1, and then I'll add here R0 minus 1, and then R 0. And then we have C P0 over Q. And this term is equal to our L over Q, and then R0, and this last term equal to our L, oops, over Q. this is equal to B and B transpose. And then this would be L transpose. Now I'm going to break this R0 to R0 1/2 to 1 0 1/2. This will equal to L over Q R0 to the power 1/2 over Q. And then from here we can determine the L. So the L will be this term, and the B, this is the transpose of it. So from here L0 will equal to Q B and R0. From here we can determine the L. So the L will be this term, and the B, this is the transpose of it. So from here L0 will equal to Q B and R0 to the minus 1. Why? Because we're going to take this number now and plug it here. Anyone lost? Or we're okay? You know, so we, from the Riccati, we just take the limit as Q goes very high, and then the resulting equation, we're going to break it. We make this R0 minus 1. And then I'll just multiply times R0 and R0 inverse, and then break it down from the equation for the gain to the gain and the gain transpose. And then we end up with this expression for the gain. Now everything is reserved for the LQG. Everything is the same because we're following exactly the same for the LQG. We did only this little trick. This little trick. And for this little trick, we make Q progressively higher. If Q is equal to 0, then we have exactly the LQG. If Q goes much higher, then this L reduces to this L. Now I'm going to take this L and plug it here and show that this reduces to this. Show that this reduces to this. Okay. Okay. So let me just put it here. And this would be our L. And then now we have identity plus the C, PC, and then the L are replaced by minus 1/2. And this whole thing is inverse. And then we multiply by C, P and B. Okay, I'll factor out the Q and R0. So this will equal to K, P, C, and then we have B, R0. And then I have here I over the Q R0 to the minus 1/2 plus C, phi C, and B and inverse. And then we have C, phi, and B. I factor Q here, so I have Q here, and I have this Q, so I have Q squared. Oops, sorry. No, we'll take this Q out, so it will be 1 over Q, and then this will be gone. Now, if Q goes higher, then this term will drop out, and we have GH, K, phi C, B, and R0. And then we have R0 also here, so this will go with R0. Okay, and then we have here C, phi C, B inverse, C, phi, and B. So we'll say this is approximate. Now I'll take these matrices and break them down like this. So we'll have here K. Oops, no, make them like this. I have two matrices like this, so the inverse will be the reciprocal of these two matrices. So I have here phi, C, and B, C, phi, and B. This will be phi, C, B inverse, and then this will be C inverse. Now this and this will be identity. This and this will be identity. And what's left is K, phi, and B.
But both are not square matrices.
Pardon?
C is not a square matrix. Phi is.
This is the only thing that requires the, that has an inverse. So this requires that C has an inverse.
But in general, it's not a square matrix.
Yeah. If it is,
And phi CB also is not a square matrix by itself. Because it's if B in general is.
but you will see now the result. Even though we violate these, you will see the result as K increases. Then we preserve this identity. Yeah, you're right. So that's the this should have an inverse, and then this should have an inverse. But also the phi C was equal to Si minus A minus Bk. And this is in the Laplace domain also. Okay? So if we do this, then we recover the LQR properties. Now the proof of this is this example. So I have here three cases. The LQR, the LQG, and the LQG with LTR. If you look at this case which we just did today, I can write Q. I break it down into some Q plus Q squared times B squared, or B transpose. My B here is 2 by 1. So when I have B transpose, so I have 2 by 1, 1 by 2. So the in between V is a scalar, and I took this scalar as 1. But you can also put this as any matrix, and then you can break it down here. V to the 1/2, V to the 1/2. So you can have again a V here. But that's the general proof for this case. But anyway, now I have this. Now I'm going to put the gain that we have is like this. So now we can calculate the gain for this case. For this Q variation, we have QF here, the R, A prime, C prime, so we can get the gain of the system. And then now, as we've done before, I can get the numerator and the denominator, and then I can plot the Nyquist plot. The same for the LQG that you've done in the homework, and the LQR. So I use the command state space to transfer function. And then once I have the numerator and the denominator, and I want to plot the Nyquist, I multiply it times the gain. And then plot the Nyquist plot. Now in the diagrams that you have a couple cases. When Q is relatively small number, the LQR is this red circle, is the red line, which is away from the -1 circle. The LQG, for any uncertainty, loses robustness and start going inside the unit circle. The LTR, because this number is not big enough, it tries to recover from this line to this line. Okay, but it's still not perfect. Now I increase this number, Q, I make it bigger. Again, the LQG as it was, and then the LQR, the red line, and then the LTR recovers, and almost on top of it when Q is very large number. Okay, and this is again the C is 1 and 0, which is not a square matrix, and then the B is 2 by 1, so the C times B is again 2 by 1. So it's not a square matrix and it's not a square. In spite of all this, you could see the recovery that you have in the characteristic. Okay, it's fine. I think I'll stop here, and then we'll begin next time on the neural network, and then the fuzzy logic. Okay? Huh? H infinity first. Okay, so before H infinity, we have to define the norms of the system. What is the H true norm and what's the H infinity norm? And then, yeah, so that's a big part. Fine, have a good evening, and please submit the exam as a homework g squared, and then I take the square root of this. Okay, so now if I write down the norm of any vector, then I get the components of the vector, square them, and add them up, and take the square root, and we have something like this. Okay, now if we're dealing with transfer functions, or responses, then I used so far this norm. Again, this is not complete. We have to add here. Square root. So this is very similar to what we've done in this general case for the LQG controller. Now, let's see how we relate this to this. And all these three controllers belong to this yellow box. And once we finish this, then we will look at another norm or another performance index, which is the H infinity norm. And the H infinity is not like this norm where I integrate. It is a norm that I look at the maximum value and try to bring it down. Here I get the square of the transfer function or the response, and then integrate them over time to bring everything, the entire integral, down. So the entire integral means that I'm looking at the function and integrate it with respect to time. So it is in effect the area under a curve. The H infinity, another type of controller. I don't look at what is going on over the entire time span. I look at a peak in the entire time span and try to squeeze it down. Okay, so now here, what is G? Okay, so this G is function of time t. Okay, we have a system looks like this. We know in the Laplace domain, I can write this equation as a response or I factor the x out and then invert, so we'll have x will equal to Si A inverse times B times U. And if we're looking at output y, then we have x, then we have y equal to C and in the Laplace domain, this is my transfer function G between output and input. look at the scalar case. This A is a scalar value. So I'll have here y is equal to c 1 over s minus small a and b and u. And we'll look at if u is equal to an impulse. Sorry. U in the time domain is an impulse. And then u in the Laplace domain will equal to 1. Okay. So now if I take this and plug it here, then we have y is equal to c b over s minus a. This is a scalar, and a scalar. Now I want to go from the Laplace domain to the time domain. So we'll do Laplace inverse. So y in the time domain will equal to c, it's a constant, and then this term in the time domain becomes exponential e to the at, and then b. Now I'm gonna take this and put it here, because this is equivalent to as if we have here u, and this u is impulse. So I have only a response given by this equation. And if we make correspondence between these two, then this is in the Laplace domain, and this box is in the time domain. So, in other words, this g of t is nothing but the time response to a unit pulse, or a unit impulse. It's very similar to what we had here. Scalar case, we're looking at the response of the system. The response of the system. But now when we look at the response of the system when I apply a unit pulse to the system. Then now I'll take this and put it here in this, and then we'll generate from it an expression for a measure for performance index. And this measure applies to the three cases that we looked at: LQR, LQG, and LQG slash LTR. So now okay, one more thing before we leave this. In the general case now, and then the output y will equal to, if it is not a scalar but it is a matrix, then this will equal to c e to the a t and b. And what I've done here is like quick and dirty type proof, okay? But the nice proof that we can do is, again, if we look at this system. Okay, if we look at this system, then has response or has solution. that I can get it from the convolution integral. Which is again e to the a t x0 plus the integral of exponential a t minus tau, and then b and u dt. Now, if the initial condition is equal to 0, which is a must for the Laplace transformation. If we want to get the transfer function of the system, we put the initial condition is equal to 0. Then this term will drop out. Then we have x will equal to this integral. I'm sorry, this is the tau. A and then I can extract from this the system output, y, by multiplying by c. Now if I have a unit impulse at time t is equal to 0, then I only have value of u at tau is equal to 0, and anything else will cancel out. So this reduces to, for unit impulse at tau equals 0, then this will give us this equation that we have. TMB. The bottom line of all this, we can write a system given by system equation and measurement. From these two, I can determine the response to a unit pulse, and this response is equivalent to the system transfer function. Let me take all this out. Then I have this system. This is my system. I don't know the A, B, and C, for example, and I want to get the response of the system, the transfer function of the system. So what would I do? I come here and inject a unit pulse. And then measure here the output. The output that I measure here is the system transfer function. So that's one way of identifying system parameters. And this is very important term. It's called the Markov parameter, also has another name. Because I can measure this at different instant of time. And if I have many samples, then I can extract the A, B, and C. So now, from what we've done so far, I have a system, and I have output measurement. I combine these two to get the transfer function of the system. We show that if I put unit impulse here, what I measure out here is nothing but the system transfer function. And in system identification, that's all what we need to identify the C, B, and A. And once we have the C, A, and B, then I have everything about the system dynamics. Okay? Now, we will use these parameters to also identify a measure of performance of the system. measure of performance of the system. Any questions? Okay. Now, and now here, the performance index, which I gave it this symbol. I gave it this symbol. This is the performance index. Some norm for measurements, some norm parameter to measure system performance. And theirs is called H2 norm. And H2, and H stands for Hardy space where this was defined. Exactly like the Euclidean norm, which is defined for vectors. This norm is defined for matrices, Because now this y can be a scalar if I have here one measurement. But this y can be a vector if I have large number of sensors and large number of actuators. So this can be a matrix. Okay. So now I can write this like G2 will equal to the trace integral, and then I have C e to the A, T, and B. And then I transform these, so this becomes B transpose E C transpose dt, and then I'll put the trace, and then I take the 1/2. And this I'll rewrite it like this integral. And then if these are constant matrices, then I can take them outside. The 1/2. And then I'm going to come and call this some name. Call it WO and then B. Called the observability Gramian, and this satisfies the following. Again, Lyapunov equation. A transpose W0, W0A will equal to minus C transpose C. And I don't think we need to prove this because we proved it 3 or 4 times already. So you just take this multiply times the integral. We have A transpose here, and then we add to it another term, same an A from here. When we add them up, we can reduce into a single derivative, and then the integral of the derivative will equal to whatever is inside. And then we put the limits when time goes to infinity, and the system is stable, A is stable. So this is just pre and post multiply W0 by A transpose A and add. And then it reduces to this Lyapunov equation. So now, how to determine then now? The H2 norm of a transfer function. You take the transfer function, G, and you can do on it a couple things, two things. Okay. I'll say here G is equal to, this is from MATLAB commands, P, C, K. This is the A, B, C, and D. So I can take the components of the system A, B, C, and D, and then pack them to form the G. And then once I have the G, then I can calculate H2 using H2 norm command of the G. Or we have the A, B, C, and I'll leave the D for a minute. Then we go and solve the Lyapunov equation. A transpose W0, W0A minus C transpose C. We have the A, we have the C, then I use MATLAB command to solve for W0. Now we have W0. Then I go here. We have W0, and we have the B and the B transpose. Get their trace. This is a matrix. Get its trace, and then get the square root. Then W0, B, and B transpose. The trace, and then get the square root. Then this will give us the. Now if we have D, and the H2 norm becomes equal to square root of the trace transpose D. And the proof of this is very simple, again, for using the same approach that we used to derive this. And the handout that I forgot to bring it to you. In this handout, I have two element rod that I represent in my two finite elements. Anyway, I have the mass and the stiffness matrix. I can assemble them and calculate the A matrix, the B matrix, the C matrix, and the D matrix. Okay? So now I have from the finite element, I can describe all these parameters, A, B, C, and D. Now I go and I want to calculate the H2 norm. The calculation, we can use this approach, use the Lyapunov command, and then the calculation of the trace component. So I use the Lyapunov A transpose. All this side is made of C transpose C. And then get the square root of the trace of this multiplication. Or use this approach, which is very fast. You have the A, B, C, and D. You form the transfer function by this command, the pack. The packing of all this in one transfer function. And then get the H2 norm by this command, H2 norm. Again, you can write down help file, and then look at this command, look at the pack command, and then of course the trace is the sum of the diagonal elements.
What's the output of PCP?
Pack is the, the output is the assembly of the transfer function in the Laplace domain. So it has special characteristic because it has more dimension than the actual transfer function because of some other reason. Okay, the bottom rows and the column are the bottom row and the last column have a special meaning. We will talk about them later on, but the construction of this is mainly how to assemble these in Laplace transform of the matrix G. Okay. So now the important thing now is the H2 norm is a measure that defines area under curve. We look at x squared, the response squared. Okay. Now the response squared of a scalar is very well known for us. Okay, when we said like x squared dt, and then I integrate, this is very clear for us. So I have the x squared here, and then I have the time here, and I have this curve. Okay, but now we don't have x as a scalar because I have transfer function. I have so many inputs, so many outputs. So I have many of these, one after the other, and I want to get all of them simultaneously. The sum of all the outputs of the system for all the inputs that's coming to the system. So now you have the entire energy coming to the system, not just a scalar, because again, this is not scalar, it is, as we said, this is a transfer function. So it has many inputs and many outputs. So now, but in effect, it's nothing but superposition of all these, and I take the amplitude squared, and the reason it is squared is it will be quadratic, and it will have a value, not 0. Okay, because if I leave this as x, then the positive will cancel the negative. Now anything positive or negative, I square it, and it is vibration. Vibration to the positive side or the negative side is vibration. If I leave it as x and integrate a sine curve, for example, with time, the result will be 0. But if I integrate the sine squared, anything that's not 0, I'm penalizing myself because it is positive vibration. So now I take the norm, which is the second norm, which is indicative of area under curve. Okay, so this is one performance index which we covered in all these three controllers. The trace operator came in the general case of the LQG when we designed the LQG controller. So now, like this norm hopefully will make sense for the LQG controller, and we could use it to determine the performance of the controller by looking at how much this value is. Okay. Now we will look at the second, a very important norm, which is H infinity norm. Before I take this out. For the example that I had on the board, if I use the Gramian approach or I used the MATLAB approach, the numbers are exactly the same. And as we'll give you the handout, then you will see the same. And the H infinity norm will study it by three methods. And this is the easiest way. I look at the response and then determine the peak response. But this requires that I have to have frequency response. I have to take the system and scan the frequencies. And it requires that I have to have all the inputs and all the output combinations. So this is very, very time consuming. Okay. The second approach is using the transfer function. I determine its eigenvalues. The transfer function, if it is a square, then it has eigenvalues. If it is a rectangle, then it does not have eigenvalues, it has singular values. So I'll use the singular value decomposition to use it, and the maximum singular value is indicative of the H infinity norm. The method that I'll start with is this method, which is the Hamiltonian matrix, which we put in the notes before, and I did not describe it in detail because now we need it very badly. So now we will use it. We will form the Hamiltonian, and the Hamiltonian has a special characteristic. And from this, we will extract from it the H infinity norm. And this is the heart of the H infinity controller. Again, you could see here, the H2 norm gives you an average value, integral over the area. So this number is very small, 5. The H infinity, look at the highest value, which is 17. So now we try to make the 17 as small as possible. I will never bring it to 5, okay, because 5 is the average over the area. But I'll take the peak value and try to squeeze it with adding the controller as much as we can. So now, if I have open loop, I get the number. I put my controller in, I get another number. Is this controller good? Yes, if the H infinity norm is minimum. Otherwise, I have to optimize the values of the control gain. This, if we learn this method very good, you can do any controller for anything. So, because here we will put constraints realistic on the system performance. How much I know A. Is that A or A plus 10%? How much I know the excitation on the system. Do I know it exactly or it has plus or minus? For example, if I have a structure that has wind loading, The wind loading can be 5 meters per second now, and it can be 7 after 2 days. It can be 5 in one direction or 5 in another direction. So I have bounds on how much I excite the system, bounds on where it comes and attack the system. So we can put all these bounds, and I can put these bounds in the time domain or in the frequency domain. So we put all this, and the final form will look like an LQG controller, exactly like what we have. And it reduces to two Riccati equation, one for the controller and one for the filter. Okay. Now the H infinity, no. And this is again a performance index. Denoting the peak response of the system. And then it's also look the same, like this. H infinity null. And then we will try to find what is the equation to calculate this. And to begin this, we'll say here, all this side notes. But the side notes might take us till the end of the class. So, and which are the again, we have a system that looks like this. With a penalty Q on the control on system vibration. Then this has the following Hamiltonian. I'm not going to prove this, but I'll put it in the note. I'll put the proofs in the note because it is it requires a lot of derivation. So I'll just put it in the note in the final form. I'll put the derivation in the notes. So this will look like this: x dot, y dot. The first variable is the state vector of the system. It has physical meaning. So this is the physical coordinates of the system, or the physical state variable. And the second line, like you will see, it has Lagrange parameter type associated with the main system because we have to satisfy, when we do the optimization, the equation of the system. So it has Lagrange multiplier and it's called the adjoint states. And this is our Hamiltonian matrix. And we'll see here the Hamiltonian. Matrix system can generate a solution. P is equal to y x inverse, where P is a solution of the following Riccati equation.
Is that the inverse of transpose?
Or inverse. Inverse
Of vector?
of a matrix. These are matrices. Okay. This is matrix. This has the physical meaning of a state vector, but it's not vector. This is matrix. This is matrix and matrix. Okay. This is matrices. We'll show you how this is generated. A transpose P plus PA minus PV R inverse B transpose P plus Q is equal to 0. The first equation will expand to give x dot a x minus y, and y dot will equal to minus qx minus a transpose y. I'm going to look first at an identity. X and x inverse, and I want to calculate its time derivative. Okay. Of course, this is identity matrix, so time derivative is equal to 0. Okay. But now I want to expand this. So this is a time function, this is another time function. So this will equal to x dot x inverse plus x d by dt x inverse, and the result is equal to 0, and this says the d by dt of x inverse will equal to minus x inverse x dot x inverse. Okay, I don't need this anymore. say here, consider the following. D by dt, y and x inverse. So this will equal to y dot x inverse plus y dx inverse by dt. So I'm going to replace y dot from here, from this. Then d by dt. And this term, I'm going to replace it by this term. So this will be P will equal to y dot is here is minus Q and X minus A T and Y, and then this whole thing is times x inverse plus y dx inverse dt. I'll replace it from here. So this will be minus x inverse x dot x inverse. If we look at what we have here, this is x and x inverse, so this will be identity and this will be minus q. This times this will be minus A transpose, and I'll replace the y x inverse by P. And then I have here y x inverse, I'll replace it by P. And then x dot, I'll replace it from here. So this will be Ax minus Br inverse B transpose y, and the entire thing now multiplied times x inverse. Now we go here, this will be minus q minus A transpose P minus P, and then I have A here times x inverse, so the two become identity matrix, and I have x here, minus and minus becomes a plus. I have P, B, R inverse, B transpose, and then the last term is y x inverse, which I combine it to be P. If P is time invariant or constant, then P dot will equal to 0, and this will equal to 0, and this equation is this equation.
It's PA, right?
Pardon?
PA.
I'm sorry. Here we have x and x inverse, so it becomes identity matrix and it becomes B and E. So now grouping the Hamiltonian in this special form, then the Hamiltonian, which again is H is equal to A minus A transpose minus Q minus B R inverse B transpose. Grouping it in this form is straightforward to extract the optimum condition for designing the controller. Okay. Now this H has special properties. Number one has eigenvalues appearing in pairs such that lambda and minus lambda are eigenvalues of H. And we will see that this lambda is also the eigenvalues of the closed loop of the system. Lambda is also an eigenvalue of the this K is the R inverse, B transpose, and P. So the bottom line of all this, if I want the closed loop to be stable, I want the eigenvalue lambda to be away from the imaginary axis, to be inside the left-hand side of the S-plane. And this is stable eigenvalue, such that we have lambda and minus lambda. So we have a stable eigenvalue and unstable eigenvalue. Because if this has negative real part, then this will have positive real part and it will be unstable. And I will show that this lambda is also the eigenvalue of the closed loop system given by this equation. So our system must have stable eigenvalues, and accordingly the lambda of H corresponding to this system has to be stable. So lambda can never lie on the imaginary axis. Lambda can never lie. And because of this criteria, we can extract the H infinity norm. First, let me just prove these two things. Let me do this.
Since the system has to be stable, that's why the real, the stable eigenvalues of H are also are the values that you're looking for P.
Yeah, we'll prove this in a minute. First proof. 1. The eigenvalue problem of H, I can write it like this. H is equal to lambda mv. So the H, this is the matrix, the eigenvalue, and then the corresponding eigenvector. Okay, that's the classical definition. Okay, now let J be a matrix like this. Okay, then J inverse, I can determine it by the cofactor dividing by the determinant. The determinant is equal to unity. The cofactor I'll flip these two and then take the conjugate, take the transpose. So this will equal to minus I and 0 and I and 0, or this will equal to minus j. Now let's look at this identity. The cofactor will be I and minus I. Okay, so I'll take this here and flip the sign so it becomes I, and then this becomes minus I, and then take the transpose. And the best proof is just multiply these two and you'll find it equal to identity matrix. Another identity that we want to use is the following identity, that H is equal to J, H transpose and J. And again, the proof of this is very simple. Just put these matrices, 0, identity, minus identity, 0, and then H transpose becomes A transpose minus B transpose R inverse B, and then minus Q, and Q is symmetric, so Q transpose is the same like Q, and then minus A, and then 0I, minus I, and 0. And the result, you will see that this result will equal to H. A minus A transpose minus Q minus B R inverse B transpose. Okay. Now I'm going to take this and this and this case. Okay, so I'm going to use these three things. So in the top equation, I'll come here and multiply times J and J. Okay, and we'll multiply here times it becomes very tight, but I'll make this here, and I'll come in between here, multiply times J and J inverse. Okay, so we did not do anything to the equation. Now, is that what I need, or no? No. It's fine. Let's see. No. We have H. I'm going to replace H by this. I'm going to replace this, so this becomes a J, H transpose J, and then V. And then here we have V and lambda. I used this last box to do this transformation. And then now, I'm going to multiply here times J and J inverse. And this becomes J H transpose, and then I have J and V, and J and V. This is eigenvalue, it's a scalar, I'll take it out. And this J inverse, I can replace it by minus J. Or we'll leave this J inverse like this. And then replace this J by minus J inverse. Okay, and I can cancel this J inverse with this J inverse. Okay, I cancel this now. And then I'll take this line. And I'll take this line. I'm going to call this cap V. And then this cap V. And then I'm going to take this minus here. H transpose. Originally, we started with this equation. And we said the matrix H has eigenvalue lambda and corresponding eigenvector V. Okay? We ended up with this equation because of the particular shape of the H matrix. What this is saying now, that H transpose has an eigenvalue minus lambda. Okay? How would we determine the eigenvalue of a matrix? For example, if I have a matrix A has 1, 0, 0, and 2. This is very easy, but if this is the matrix, then the eigenvalues are 1 and 2. Okay? If I transpose this matrix, it still has the same eigenvalues. Why? Because to get the eigenvalues, I have to set the determinant of lambda I minus A is equal to 0. The determinant doesn't care if I expand from the row or I expand from the column. The determinant is the same. So the determinant of A is the same as the determinant of A transpose. So the eigenvalues of A are exactly the eigenvalues of A transpose. So because of this fact, when I expand, the determinant, it doesn't care if I expand from here or I expand from the row, the column or the row. Then this is the same as the determinant lambda I minus A transpose. And the bottom line of this, A and A transpose have the same eigenvalues. So now here, H and H transpose have the same eigenvalues. H has eigenvalue lambda, H transpose has eigenvalue minus lambda, then lambda and minus lambda are eigenvalues of H and H transpose. And here the conclusion of all this, lambda and minus lambda are both eigenvalues of H. Okay. So this is the first item. Second item now. Of course, the positive and negative eigenvalues have different eigenvectors, V and cap V. Again, if you remember, this was given like this. I'm going to expand only the top row. And y. Okay? But we have the control gain is equal to, first we have P is equal to y and x inverse. Okay? And the control gain is equal to times P. So I can now replace this y and x inverse. If I want only this, then and y. So now I can take this and replace it by kx. And I can take this here, right here. So this now will be equal to A, and then I have x here. And then I have B, K, and x. So I'll factor out the x out. Okay, then we don't need all this. And now here, the closed loop. We have here x dot is equal to a closed loop and x, or AC. X has eigenvalues x. And in the same way, I can restructure this with the y. So we have minus lambda, same story here. So the assembly of this and this is the H matrix. So then this, we'll say here the eigen value of AC is lambda, which is same as each eigenvalue. Then now, to have a stable eigen value for the closed loop, requires that H also have stable lambda. Okay, and the final conclusion of all this if lambda is stable, then H does not have any eigenvalues on the imaginary axis. And this conclusion is what we're going to use to calculate the H infinity norm. The H infinity norm unfortunately has another Hamiltonian matrix. Oh boy. I'm very sorry. So we're over 10 minutes, huh? I'm sorry, so I'll give you a refund. It's fine, have a good evening.